Welcome back. I'd like to talk about time-reversed system today. Using the time-reversed system idea, we'll be able to show something pretty interesting by the end of this segment. And this time-reversed system idea is very simple. So consider a queuing system that here the x-axis is showing the time axis as time increases, and this y-axis is just the number of packets in the system. And then we have an arrival here. Basically, we have one packet in the system, and then an arrival, an increase of number of packets, another arrival here, and then departure, 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 and then there's nothing left in the system. So for the time reverse system, basically we are looking at the time running backward. So then in this case, the departure will look like an arrival. So going backward, this one is like an arrival, another arrival, another arrival, and then a departure, departure, departure. So here I'm just redrawing this time reverse system, basically just flipping the time axis. So what then? Let's consider, let's say, for this time reverse original system, just assume that we can draw the state diagram of the original system. So we have couple states, let's say have like from some 0 to 1, state 0, 0 to 1, and 1 to 2, and so on, and then going backward. For example, for MM1, remember this transition probability would be just lambda delta, something like that. Here we would do it pretty generally. We would just write something the transition probability as P01, and this transition probability P12, and this is P21 and P10. Now, let's say let's look at the transition probability from state I to j, for example, Pij of the original system. Pij will be basically, if I write it more explicitly, will be the probability that when the original state at, let's say, time m is equal to state I, and then xm plus 1, it becomes j. And I can just use the base rule. This probability will be just equal to p xm plus 1 equal to j, xm equal to I over x probability xm equal to I. So then I can use the base rule again. I can rewrite this as xm equal to I given xm plus 1 equal to j, and p xm equal to j over p xm equal to I. But let's see, what is this probability here? This is the probability that given at the next time instance that the state is equal to j, what's the probability that the current state is equal to I? So then basically this is really the transition probability of the time reverse system. Let me denote that as P star as the Ji is the transition probability of the time reverse system from j to I. Then this is just P star Ji, or like maybe I can just write P star Ji times P xm equal to j is equal to Pij P xm equal to I. So this is true for every m, basically, every time instant m. And of course, if we have the transition, if we have the steady state probability pi, denoted as pi I, this is a steady state probability of state I. So the steady state probability just meaning that like this pxm equal to I, that when m goes to infinity, like it converges to some kind of like just the probability is not changing anymore. Then of course in that case we also have Pij. Generally this also hold like for m goes to no matter what m is. So therefore we in general for, or I should say in particular, I have this actually. That is for the given the steady state probabilities, we can relate the transition probability of the forward system with the transition probability of the reverse system. And this is kind of true for any system that we can draw the state diagram and with the transition probabilities that can be specified. Okay, recall that for pi 1, maybe start with pi 0, pi 1, pi 2, and so on, these are the steady state probability if and only if it satisfies the conditions that for all this, for any I have pi I is equal to pi j pji times sum over j. So it makes lots of sense. Think of like this pi j is not steady, for example, like or like this pi j is just the probability of state j at the moment. And then like pji, if pi j multiplied by pji will be all the probability fall into state I. So this thing on the right hand side will be the probability of state I in the next time instance, really. So of course like pi I will be steady only if in the next time instance will be still equal to the current probability pi I. And it has to hold for every I. If that is true, then apparently this is the steady state probability. So now what I want to show is that for the time reversed system, pi I, that's basically the steady state probability of the forward system, will also be the steady state probability for the reverse system. So therefore we actually want to show that pi j pji star sum over j should be equal to pi I also. That's, we don't know, but we want to show this. So let's see, on the left hand side that we have pi j pji star sum over j, and pji star we know that is just equal to pij pi I over pi j, right? So we just substitute into that. We've got pi j go cancel, and then what we see here is basically pi I has nothing to do with j. We are summing over j, so we can just pull over pi I here. So we sum over j pi I j, and pij is the transition probability from state I to state j, and we are summing over to all j. Of course this should sum out to 1 because this probability need to transit to somewhere. So if we sum over all the possibilities, it's to sum over to 1, so therefore it is equal to pi I. So that shows that this is equal to right hand side. So therefore we really have like pi i's maybe the steady state probability for the reverse system. Okay, we have this one here that is saying that like the steady state probability for the forward system is the same as the steady state probability for the reverse system. And remember that like for most of the systems that we study, they satisfy the detailed balance equation. That's basically for two states, the transition probability from one state to another state, let's say from I to j, or like I should say the probability flow from I to j, basically is pij times pi I, let's say at the steady state, is equal to the probability that going back into state I is equal to pi j pji. This is just recall actually. Recall if pi I pij is equal to pi j pji, this is what we call detailed balance equation satisfy. So if this is the case, remember that we also have this equation here that is true for all systems. So, and if we compare this here, you see that like pij, pi I should also equal to pji pi j. So we have pji pi j is actually equal to pji star pi j, and this is true for all imj. So then we can just cancel this pi j here. So it's actually saying that the transition probability is the same also if the time reverse. This is another property, let me just write it here. If detailed balance equation satisfied, maybe I can just put another. Then actually I should write it as if and only if. If this is true, then we have pij or pji, doesn't matter, will be equal to pij star also. So the transition probability of the reverse system is the same as the transition probability of the forward system. And note that like these transition probabilities really specify the entire state transition diagram in terms of specify all the statistics of the system. So therefore, essentially, if you have the detailed balance equation is satisfied, the time reverse system is essentially the same as the forward system in terms of like the statistics underneath it. And by the way, when the detailed balance equation is satisfied, we also call the system time reversible in the sense that like when the reverse system will be time reverse system statistically will be the same as the original system. Now, what I'm going to do is like I want to show a rather interesting theorem known as the Burke's theorem. It can be easily derived from what we have discussed just now, about using properties of the time reversible time reverse system and time reversible idea. So basically what the Burke theorem is saying is that if the system is time reversible, then the followings will be true. First, the reverse system will be Poisson and with an arrival weight lambda, or in other words, the original system will have a departure process is basically Poisson with weight lambda. So let's think of let's say any time reversible system, let's say MM1Q. What it's saying is that let's say we have the arrival weight lambda and the surface rate mu. If you look at the statistics of the departure, it will look like just a Poisson process with departure rate lambda. And this is rather obvious from our discussion, as if the system is time reversible, in this case it is because the detailed balance equation is satisfied, then in the time reverse system, it will be identical to the original system statistically. So therefore, it will also have the arrival weight is lambda. And of course, if we translate this back to the original system, it corresponds to the departure weight will be lambda. And that's just part A here. Maybe I put it. And secondly, if a system is time reversible, the number of packets or customers in the system at time t will be independent of the departure time before t. Okay, this is a pretty mouthful statement, but just look at this example here. What it's saying is that here I also draw the number of packets in the system, like over a period of time. Let's say at this particular time t, the number of packets, that's basically 2 here, will be independent of the departure time before it. So it's independent of this event here. It's actually not really very intuitive. It's really counterintuitive, I would say, because intuitively I would think that if you have if the system just have a loss of departure, let's say, then it seems like that it will be more likely to have fewer packets in the system at time t. So therefore, it doesn't look like the departure time before t should be independent of the number of packets at time t. But of course, another way to think of that is, wait a minute, because if we only consider the departure time, maybe before that there's a lot of packets in the system already. Maybe some is leaving from the system, so there, but still there are a lot of that. So therefore you can't really tell. So probably that will be an argument why this is independent also. But from the point of view of time reversible system, it's very easy to show, because if we consider the time reverse system that's basically just flipping everything, like arrival into departure and before become after, our statement here for the reversible system will just translate to the number of packets at the system at time t is independent of the arrival time. Now departure become arrival time after t. So maybe I should just write in red here. For the reversible time reverse system, they will become arrival time after t. And of course, we expect the number of packets in the system at time t will be independent of the arrival time after t. So therefore, this statement will be true also. But we have to be very careful that if we modify the statement a little bit, it probably won't be true anymore. For example, if we change this departure time to arrival time, then what happens is we need to change to in the time reverse system, now the arrival time here, arrival time here in the time reverse system, it becomes departure time. And of course, the departure time after time t will depend on the number of packets at time t. Because if there's no packet in the time t, then of course there will be no departure after time t. Given that there's no arrival also. So, I mean, it won't be, at least it won't be completely uncorrelated as in the case earlier. So, therefore, like, anyway, we just should have to be very careful about the statement. But what I want to say just in summary is this time reversible idea is pretty interesting, because using that, just I guess 20-30 minutes of discussion, we can show something is rather non-trivial really.